We begin with a classical construction from Euclid's Elements. In a semicircle, drop the perpendicular from point C to the diameter at D. If AD is A and DB is B, then the claim is that CD is the geometric mean. CD equals the square root of AB. This is not merely a clever exercise. It belongs to the old Euclidean theory of mean proportionals. Let the point C move along the arc. The altitude changes, and the two pieces of the diameter trade length. Yet the relation we seek remains the same. The moving picture suggests an invariant, but the proof must explain why it is invariant. The argument will proceed in the most classical way possible. We do not chase an external construction. We look inside the figure, identify two right triangles, and prove that they are similar. Once the similarity is established, the mean proportional appears by proportion alone. Euclid gives this point of view in the Elements, Book VI. In Proposition 8, the altitude from the right angle produces triangles similar to the whole and to one another. In Proposition 13, the same semicircle figure becomes a straight edge and compass construction of the geometric mean. So this picture is not a modern trick. It is part of the original Euclidean grammar of proportion. Now we begin. Because AB is a diameter and C lies on the circle, angle ACB is a right angle by Thales' theorem. That single right angle is what allows the entire configuration to break into comparable pieces. Now drop the perpendicular from C to the diameter at D. That altitude splits the big right triangle ACB into two smaller ones, triangle ADC on the left and triangle CDB on the right. Both have a right angle at D. Next comes the decisive angle comparison. In triangle ADC, the acute angles are complementary to the right angle at D. From the larger right triangle, the same complementary relation appears at C. Therefore, angle DAC equals angle DCB. One acute angle in the left triangle matches one acute angle in the right. Now the conclusion is immediate. Each triangle has a right angle at D, and we have just matched one acute angle. Two angles agree. Therefore, the triangles are similar by AA. The whole Euclidean mechanism is now in place. Watch the similarity in motion. The blue triangle pivots about D, shrinks, and comes to rest on the orange triangle. One vertex stays fixed, one side changes scale, and the angle structure is preserved throughout. The animation is not the proof, but it makes the proportional correspondence visible. From similar triangles, corresponding sides are proportional, so AD over CD equals CD over DB. This is the exact Euclidean form of a mean proportional. The middle length stands between the other two as an extreme and a mean. Now cross-multiply. CD squared equals AD times DB. In our notation, CD squared equals AB, and therefore CD equals the square root of AB. The altitude is precisely the geometric mean of the two segments of the diameter. Return once more to the moving figure. The two smaller triangles keep changing shape, but the proportional relation survives every position of C on the arc. That is why the theorem belongs naturally to Euclid's theory of similarity, not to one accidental drawing. So the old Euclidean argument is complete. The semicircle, the right angle, the pair of similar triangles, and the mean proportional all belong to one coherent picture. This is why the theorem has remained so durable. The proof is short, exact, and entirely geometric.